Good evening and welcome. I'm Dr. Maren Solis, and I'm glad you've joined us. What you're about to hear is the story of our ocean, where it came from, how it shaped everything we know, and why its history matters today. So, get comfortable and let's dive in. 4.5 billion years ago, Earth had no ocean, no water at all. The whole planet was just melted rock, poisonous air, and constant meteor strikes. Nothing like the world we know today. So where did all the water come from? It sounds like a simple question. Water has always been here, right? Actually, no. And figuring out where it came from is one of the most fascinating mysteries in the history of our planet. Scientists have two main theories, and the evidence suggests that both of them are probably right. The first theory is that the water came from space. About 4 billion years ago, Earth was being hit constantly by comets and asteroids flying in from the far edges of our solar system. A lot of those rocks had water frozen inside them. Every time one hit the Earth, that water was released as steam into the air. Over millions of years, as the planet slowly cooled down, that steam turned into clouds. And then it rained. Not just a rainstorm, but a non-stop, planet-wide downpour that went on for thousands of years. Slowly, water began pooling in the low points of the Earth's surface. And that was the beginning of the ocean. The second theory is that Earth was actually making its own water. The inside of the young Earth was incredibly active, and volcanoes were everywhere. Volcanoes don't just throw out lava, they also release gases. And one of those gases is water vapor. Over billions of years, enormous amounts of water vapor rose up from deep inside the Earth and made its way into the atmosphere. Most scientists now believe it was a combination of both. Some of Earth's water bubbled up from within the planet itself. Some of it arrived on rocks from space. Together, over an almost unimaginable amount of time, they filled the great low basins of the Earth's surface. And roughly 4 billion years ago, the ocean was born. But here's what's interesting. The ocean that existed 4 billion years ago looked absolutely nothing like the one we know today. It wasn't blue, it wasn't full of life, and if you could somehow dip your hand into it, you would not recognize it as water at all. The early ocean was incredibly hot, not quite boiling, but close. The only reason it stayed liquid was because the air pressure back then was so heavy that it kept the water from evaporating. On top of that, it was extremely acidic, full of dissolved iron, sulfur, and carbon dioxide. Think of it less like water and more like a very weak acid. And there was zero oxygen anywhere, not in the water, not in the air. The gas that all animals need to breathe simply did not exist yet. Here's another surprising thing. Back then, there was almost no dry land either. The Earth's crust was still very thin and still being formed. It was constantly being torn apart and rebuilt by the intense heat churning underneath it. The continents as we know them didn't exist. Instead, the ocean covered almost everything, broken up only by small volcanic islands poking above the surface here and there. Scientists have a name for this earliest period of Earth's history. They call it the Hadean, after Hades, the underworld in Greek mythology. And the name really does fit. It was a world of extreme heat, constant volcanic eruptions, crushing pressure, and non-stop chaos. And yet, in the middle of all of that, something was about to happen that would change everything. Something so small you couldn't even see it with the naked eye, but something that would eventually transform not just the ocean, but the entire planet. When scientists try to figure out where life first appeared on Earth, most of them don't point to dry land. They point to the bottom of the ocean, specifically to cracks in the ocean floor called hydrothermal vents, places where superheated water, loaded with minerals, shoots up from deep inside the Earth. These vents create a natural chemical reaction between the hot vent water and the cold ocean water around it. And that reaction produces energy, a tiny but constant source of energy. And energy, given enough time, is all life really needs to get started. At least 3.7 billion years ago, and possibly much earlier, the first signs of life show up in the rock record. Not animals, not plants, just thin layers of microscopic organisms clinging to rocks on the shallow ocean floor. These are called stromatolites, basically just slow-growing mounds built up over thousands of years by communities of microbes. Fossils of these tiny organisms have been found in ancient rocks in Australia and Greenland, and they are some of the oldest signs of life ever discovered on Earth. They don't look like much, but what they were doing would eventually change the world completely. These tiny organisms had figured out how to photosynthesize. In other words, they learned how to use sunlight to make energy for themselves, the same basic process that every plant on Earth uses today. And as a byproduct of that process, they released oxygen. At first, just tiny amounts. But over hundreds of millions of years, more and more oxygen built up. For a long time, the ocean soaked it all up. The iron dissolved in the water reacted with the oxygen and sank to the seafloor, creating thick layers of iron-rich rock that we still mine for steel today. But eventually, the ocean couldn't absorb anymore. The oxygen started leaking out into the air. And when that happened, it set off a chain of events that would be the biggest turning point in the history of life on Earth. Take a moment to think about what has already happened. In just over 1 billion years, a dead, waterless rock became a planet with a global ocean. And somewhere in that hot, acidic, oxygen-free sea, life quietly got started. What began with steam and falling rocks had become something alive, something that had no idea what it was about to become. The ocean's story had only just begun. To understand what happens next in our story, there is one thing worth keeping firmly in mind. When oxygen started building up in the atmosphere, roughly 2.4 billion years ago, life had already been around for well over 1 billion years. This was not the beginning of life. Life was already established, already widespread, already covering the ocean floor in thick microbial mats and drifting through the water in countless billions of cells. The ocean was, by this point, a living world. It just wasn't a world that had any oxygen in it. And that matters enormously, because every single living thing on Earth at that time had evolved in a world without oxygen. Their entire biology, every chemical process that kept them alive, was built around the absence of it. Oxygen wasn't something they used. For most of them, it was something that actively damaged their cells. Think of it this way. Imagine if the air you had breathed your entire life suddenly started filling up with chlorine gas. That's roughly what the rise of oxygen meant for the organisms that were alive at the time. So where was all this oxygen coming from? The answer is the cyanobacteria, a type of bacteria that had developed the ability to photosynthesize. In other words, they had learned how to use sunlight to make energy for themselves. And as a byproduct of that process, they released oxygen into the water and eventually into the air. they had been doing this for hundreds of millions of years. In a twist that is almost darkly funny, these tiny organisms were slowly poisoning every other living thing around them, completely unintentionally, simply by doing what they did to survive. They had no idea what they were causing. They were just making energy from sunlight and releasing oxygen as a byproduct, the same way they always had. But the cumulative effect, over hundreds of millions of years, was catastrophic. For a long time, the ocean absorbed the oxygen before it could cause too much damage. Iron dissolved in the seawater, reacted with the oxygen, and sank to the seafloor, locking it away in thick layers of iron-rich rock. We still mine those rock formations for steel today, but eventually the ocean ran out of iron to absorb it with. The oxygen had nowhere left to go. It began building up in the atmosphere. As oxygen levels climbed, the vast majority of microbial life on Earth was wiped out. The organisms that had dominated the ocean for over 1 billion years, the archaea, the anaerobic bacteria, the ancient single-celled creatures that had no use for oxygen, died off in enormous numbers. This event is called the Great Oxygenation Event, and it stands as the largest extinction in the history of life on Earth. Not the most famous. That title tends to go to the asteroid that killed the dinosaurs. But in terms of the sheer proportion of living things destroyed, nothing else comes close. However, and this is the part that makes the story remarkable, not everything died. A small number of organisms survived, either by retreating into oxygen-free pockets of the deep ocean where conditions hadn't changed, or by doing something even more extraordinary. They adapted. They figured out how to tolerate oxygen. And then, over time, they figured out how to use it. Using oxygen to power your body turns out to be dramatically more efficient than not using it. It's like the difference between a campfire and a jet engine. Both burn fuel, but one does it with far greater power and efficiency. Organisms that could breathe oxygen had access to far more energy than those that couldn't. Over time, they had a massive advantage. They grew more complex. They developed new capabilities. They became the ancestors of every animal, every plant, and every complex living thing that has ever existed on this planet, including every creature in the ocean today, and including us. So the Great Oxygenation Event was two things at once. It was the greatest mass extinction in the history of life, and it was the starting gun for all complex life on Earth. Without it, none of what follows in this story would have been possible. But before complex life could truly take hold, the ocean had one more trial to endure. A trial so extreme, so all-encompassing, that it is almost impossible to imagine. The Earth was about to freeze. Completely. Around 700 million years ago, the planet entered a period that scientists call Snowball Earth. The name is exactly what it sounds like. The entire planet, from the poles all the way to the equator, was covered in ice. At least that's the theory. The oceans didn't just have ice caps at the poles. They froze over entirely, in some places under a layer of ice that may have been several miles thick. The surface of the Earth would have looked from space like a giant white ball. How did this happen? It was actually a chain of events. At the time, most of the Earth's land mass was clustered near the equator. When rocks are exposed to rain, they absorb carbon dioxide from the atmosphere through a process called weathering. With so much land near the equator, where rainfall is heaviest, enormous amounts of CO2 were being pulled out of the atmosphere. CO2 is a greenhouse gas, meaning it traps heat. As levels dropped, the planet started to cool. Ice began to form. And here's the cruel twist. Ice is white, and white surfaces reflect sunlight rather than absorbing it. So the more ice formed, the more sunlight bounced back into space, and the colder the planet got. It became a runaway cycle that was almost impossible to stop. The question scientists debated for years was, how did anything survive? If the entire ocean was frozen solid, everything should have died. The answer, once again, comes back to the hydrothermal vents we talked about in the early ocean. Deep beneath the ice, in pockets of liquid water kept warm by heat rising from the Earth's interior, life held on. It was dark, cramped, and extraordinarily difficult. But it survived. The escape came from volcanoes. Sealed under ice, the normal processes that pull carbon dioxide out of the atmosphere were completely shut down. But volcanoes kept erupting regardless. And volcanoes release CO2. With no way for the gas to be absorbed, it built up in the atmosphere over millions of years until the greenhouse effect became so powerful that it cracked the ice. The melt that followed was rapid and dramatic. Temperatures swung wildly. The ocean flooded with meltwater, loaded with nutrients that had been locked in the ice for millions of years. And in that sudden rush of warmth, light, and nourishment, life didn't just recover, it exploded. About 540 million years ago, something happened in the ocean that scientists still argue about today. In a relatively short window of time, geologically speaking, the ocean went from being dominated by simple, mostly microscopic life to being packed with an extraordinary variety of complex animals. Animals with eyes, with shells, with legs, claws, mouths, and nervous systems. Almost every major group of animals alive on Earth today can trace its roots back to this one period. Scientists call it the Cambrian Explosion, and it is one of the most dramatic and puzzling events in the entire history of life. To understand just how sudden this was, think of it this way. If you compress the entire history of life on Earth into a single 24-hour day, simple microbial life would dominate for the first 21 hours. Then, in the final 3 hours, complex animals would suddenly appear. The Cambrian Explosion is that moment, a burst of biological creativity so rapid and so dramatic that it fundamentally changed the ocean forever. Nobody is entirely sure what triggered it. Some scientists point to oxygen levels finally reaching a threshold that made complex animal life possible. Others point to the end of snowball Earth flooding the ocean with nutrients. Some think it was a combination of factors that all came together at the same time. Whatever the cause, the result was an ocean teeming with life unlike anything that had existed before. The creatures of the Cambrian Ocean were extraordinary, and many of them were deeply strange. One of the most well-known is the trilobite, a hard-shelled creature, a bit like a modern horseshoe crab, that came in hundreds of different shapes and sizes and crawled across the ocean floor in enormous numbers. Trilobite fossils are found all over the world and are often the first fossils people ever find because they are so abundant and so well preserved. But the trilobite was just one of many remarkable creatures. There was Anomalocaris, the apex predator of the Cambrian Ocean, a creature that could grow up to 3 feet long, with large compound eyes and circular jaw-like appendages at the front of its body. It was the largest animal alive at the time, and nothing else in the Cambrian Ocean wanted to encounter one. There was hallucigenia, a tiny creature covered in spines that was so bizarre that when scientists first found its fossils, they couldn't agree on which end was the head or even which side was the top. And there was Opabinia, which had 5 eyes and a long, flexible snout ending in a claw, and which looked like nothing that has ever existed before or since. The best record we have of this incredible world comes from a site in Canada called the Burgess Shale, a fossil deposit in the Rocky Mountains of British Columbia, where an entire Cambrian ecosystem was preserved in extraordinary detail. The fossils found there have given scientists a window into a world that would otherwise be completely lost to time. Soft-bodied creatures that would normally leave no trace were preserved perfectly, right down to their internal organs. It is one of the most important fossil sites ever discovered. Most of the strange body plans that appeared during the Cambrian didn't survive. Evolution was running at full speed, testing every possible design. Most of those experiments failed, but the ones that worked became the foundation for everything that followed. The basic body plans of fish, insects, worms, mollusks, and every other major group of animals alive today were all established during this one remarkable period. The Cambrian Explosion didn't just fill the ocean with life. It set the template for all animal life on Earth. Over the hundreds of millions of years that followed, the ocean kept changing and evolving. New species appeared. Old ones disappeared. 5 major mass extinctions struck. Events so severe that they wiped out the majority of species alive at the time. Each one was followed by a slow, painful recovery during which new animals evolved to fill the spaces left behind. The ocean is not a stable, permanent thing. It never has been. It is a constantly changing system, always in the process of becoming something new. Up to this point in our story, we've been talking mostly about what lives in the ocean. But the ocean doesn't just contain life, it shapes the entire planet. The land we walk on, the weather we experience, the climate that makes life on Earth possible, all of it has been fundamentally influenced by the ocean. To understand how, we need to talk about 2 things: plate tectonics and ocean currents. Let's start with plate tectonics. The surface of the Earth is not one solid piece. It's made up of large sections called tectonic plates, like the pieces of a cracked eggshell that sit on top of the hot, partially molten rock of the mantle below. These plates are constantly moving incredibly slowly, about as fast as your fingernails grow. But over millions of years, that slow movement adds up to enormous changes. The engine that drives this movement is largely the ocean floor. At places in the ocean called mid-ocean ridges, underwater mountain chains that run for tens of thousands of miles, new ocean floor is constantly being created as molten rock rises up from the mantle and solidifies. This pushes the plates apart. At the same time, at other places called subduction zones, old ocean floor dives back down into the mantle, dragging the edges of continents with it. This is what builds mountain ranges, causes earthquakes, and powers volcanic eruptions. What this means is that the continents have not always been where they are today. About 250 million years ago, all of the land on Earth was joined together in one enormous supercontinent that scientists call Pangaea, surrounded by a single vast ocean. Then slowly, Pangaea began to break apart. The pieces drifted away from each other, carried on their tectonic plates. New ocean basins formed between them. The Atlantic Ocean, for example, simply did not exist 200 million years ago. It opened gradually as North America pulled away from Europe and Africa pulled away from South America. Today, the Atlantic is still growing, widening by about an inch every year. This constant rearrangement of the continents has had enormous consequences for life in the ocean. Every time a new ocean basin opens or closes, it changes circulation patterns, alters temperatures, and creates or destroys habitats. The rise of the Isthmus of Panama, the narrow strip of land connecting North and South America, happened about 3 million years ago when the seafloor pushed up far enough to close off the connection between the Atlantic and Pacific Oceans. That single geological event changed ocean circulation so dramatically that it may have helped trigger the ice ages that followed. Now let's talk about ocean currents, because this is where the ocean's influence on our everyday climate becomes most direct. The ocean is constantly moving, driven by differences in temperature and saltiness. Warm water is less dense and floats near the surface. Cold water is denser and sinks. Saltier water is denser than fresher water. These differences in density drive a massive planet-wide circulation system that scientists call the thermohaline circulation, or more simply, the global ocean conveyor belt. Here is how it works. Warm surface water near the equator flows north and south toward the poles. As it travels, it releases heat into the atmosphere, warming the air above it. When it reaches the polar regions, it cools down, becomes denser, and sinks to the ocean floor. That cold, dense water then flows slowly along the bottom of the ocean basins, travelling across the globe until it eventually rises back to the surface in other parts of the world, a process called upwelling, and the cycle begins again. The whole loop takes roughly 1,000 years to complete. This conveyor belt is one of the most important systems on Earth. It distributes heat around the planet, keeping some regions far warmer than they would otherwise be. Western Europe, for example, sits at the same latitude as much of Canada. But thanks to the warm Atlantic current, known as the Gulf Stream, its climate is dramatically milder. Without the ocean conveyor belt, large parts of Europe would be far colder and far less hospitable than they are today. The conveyor belt also distributes nutrients through the ocean. When cold, deep water rises to the surface through upwelling, it brings with it nutrients that have sunk from the surface over thousands of years. These nutrient-rich zones are some of the most productive fishing areas in the world, places where the ocean teems with life because of the constant supply of food being pumped up from the deep. The ocean and the atmosphere are not two separate systems. They are deeply and intricately connected. What happens in the ocean affects the weather above it. What happens in the atmosphere affects the circulation of the ocean below. Together, they form the climate engine of our planet. And understanding that connection is increasingly important because right now that engine is changing in ways it has not changed before. For most of human prehistory, the ocean was a boundary, a wall at the edge of the known world. Our earliest ancestors spent their lives on land, following animal herds and moving between rivers and forests. But somewhere along the way, something changed. We started paying attention to what was on the other side of that boundary, and eventually we stepped into it. The earliest evidence of humans using the ocean comes from the southern coast of Africa at a site called Pinnacle Point, dating back around 160,000 years. There, archaeologists have found ancient piles of discarded shellfish shells, which tells us that early humans were collecting and eating seafood in a systematic way, long before any other evidence of complex behavior shows up in the record. Shellfish are an incredibly rich source of protein and nutrients, and many scientists believe that access to this coastal food source may have played a role in the development of the modern human brain. The ocean didn't just feed our ancestors. It may have helped make us who we are, but eating shellfish on the shore is a long way from sailing the open ocean. That leap took much longer. And when it finally happened, it was arguably the most daring thing any human being has ever done. The Polynesian people are widely considered the greatest maritime navigators in human history. Starting around 3,000 years ago, they set out from the islands of Southeast Asia in large double-hulled canoes, and over the following centuries colonized an enormous triangle of the Pacific Ocean, stretching from Hawaii in the north to New Zealand in the south to Easter Island in the east. These are some of the most remote islands on the face of the Earth, separated by thousands of miles of open ocean. And the Polynesians found them, settled them, and built thriving communities on them. Without compasses, without maps, without any of the navigational instruments we would consider essential today. How did they do it? They navigated by the stars, using the positions of specific stars at specific times of year to determine their direction. They read the ocean swells, the long rolling waves generated by distant weather systems, which travel in consistent directions and can be felt even on a cloudy night when the stars aren't visible. They watch the behavior of birds, which fly toward land to roost at dusk. They observed cloud formations, which tend to form over islands because of the heat the land generates. They were not guessing. They had developed a sophisticated science of ocean navigation passed down through generations that allowed them to cross the world's largest ocean with remarkable accuracy. While the Polynesians were mastering the Pacific, other civilizations were building trading empires on different oceans. The Phoenicians, a civilization based in what is now Lebanon, mastered the Mediterranean Sea around 1000 BC, establishing trade routes that connected the Middle East, North Africa, and southern Europe. Arab traders built networks across the Indian Ocean, connecting the Middle East, India, and East Africa in a web of commerce that moved spices, textiles, gold, and ideas across thousands of miles. Chinese fleets under the Admiral Zheng He ventured as far as the east coast of Africa in the early 1400s, decades before European explorers had worked up the courage to sail south of the Sahara. Then came the European age of exploration, and it changed everything. When Portuguese sailors began pushing down the coast of Africa in the mid-1400s, they were looking for a sea route to Asia that would allow them to bypass the overland trade routes controlled by Arab merchants. What they found was a world that Europeans had no idea existed. In 1492, Christopher Columbus crossed the Atlantic and reached the Caribbean. In 1498, Vasco da Gama rounded the southern tip of Africa and reached India by sea. In 1522, the last survivors of Ferdinand Magellan's expedition completed the first circumnavigation of the globe, proving once and for all that the Earth was round and that the oceans were all connected. These voyages triggered one of the most consequential periods in human history. The exchange of goods, people, animals, plants, and diseases between the Old World and the New, known as the Cambrian Exchange, reshaped societies on both sides of the Atlantic. The ocean was the highway through which all of it travelled. It was also the route through which potatoes, tomatoes, corn, and chocolate reached Europe, and horses and cattle reached the Americas. The modern world, its food, its culture, its borders, and its inequalities, was largely shaped by what moved across those ocean routes in the 15th, 16th, and 17th centuries. To understand the history of humanity, you have to understand the history of the ocean. The two stories are inseparable. For all of those centuries of seafaring, for all the trade routes, the naval battles, and the epic voyages of exploration, humanity spent almost no time actually trying to understand the ocean itself. Sailors knew the surface. They knew the currents and the winds and the stars. But what lay beneath the waves was almost completely unknown. The deep ocean was, for most of human history, simply a mystery, and for a long time nobody was particularly motivated to solve it. That began to change in the mid-1800s. The expansion of global telegraph communication created a sudden practical need to understand the ocean floor, because laying underwater telegraph cables required knowing what the bottom actually looked like. Engineers needed to know how deep the water was and whether the seafloor was flat enough to lay a cable on. For the first time, there was a commercial reason to study the deep ocean. And what they found when they started looking surprised everyone. In 1872, the British Royal Navy converted a warship called HMS Challenger into the world's first dedicated oceanographic research vessel. Over the next 4 years, the Challenger sailed nearly 70,000 nautical miles across every ocean on Earth. Its crew dropped a weighted line over the side at hundreds of locations to measure the depth of the water, a painstaking process that could take hours at each site. They collected water samples from different depths. They dragged nets along the seafloor and hauled up creatures that no human being had ever seen before. They measured temperatures, salt levels, and currents throughout the water column. The results were astonishing. The ocean floor was not a flat, featureless plain as most people had assumed. It had mountains, it had valleys, it had vast plains and dramatic ridges. At one location in the Pacific, the weighted line just kept sinking deeper and deeper until it finally reached bottom at nearly 27,000 feet below the surface. That location is now known as the Challenger Deep in the Mariana Trench, and it remains the deepest known point on Earth. The Challenger expedition produced 50 volumes of scientific reports and is widely credited with inventing the science of oceanography, the systematic study of the ocean as a whole. But knowing the depth of the Mariana Trench is one thing. Actually, going there is something else entirely. It took another 88 years before any human being laid eyes on the deepest point on Earth. In January 1960, 2 men, Swiss oceanographer Jacques Piccard and US Navy Lieutenant Don Walsh, climbed into a small steel vessel called the Bathyscaphe Trieste and began the 5-hour descent to the bottom of the Challenger Deep. The pressure at that depth is over 1,000 times greater than at the surface, enough to crush a standard submarine like a tin can. The Trieste's observation window cracked on the way down, filling the cabin with a sound like a cannon shot. They kept going. When they finally reached the bottom, nearly 7 miles below the surface, they looked out through their porthole and they saw a flatfish, a living creature resting calmly on the sediment of the deepest, most remote, most extreme environment on the planet. That single observation changed everything. If life could exist there, then the boundaries of where life could survive were far wider than anyone had imagined. It reframed our understanding of biology, and it opened a line of thinking that shapes how we search for life on other worlds today. Since then, every decade has brought new discoveries from the deep. In 1977, scientists diving in the submersible Alvin off the Galapagos Islands discovered something nobody had predicted: entire ecosystems clustered around hydrothermal vents on the ocean floor, tube worms 6 feet long, ghostly white crabs, dense communities of clams and mussels. All of them living in complete darkness, in scalding water loaded with toxic chemicals, powered not by sunlight, but by the chemical energy of the vents. It was the first ecosystem ever discovered that had no dependence whatsoever on the sun. It rewrote the textbook definition of life. Today, the deep ocean remains the least explored environment on Earth. We have mapped more of the surface of Mars than we have of our own ocean floor. Less than 25% of the seafloor has been mapped in high resolution. Every time a new expedition ventures into the deep, it returns with species that have never been seen before. The ocean is 4 billion years old, covers most of our planet, and we have barely begun to understand it. The ocean has survived a lot. It survived the asteroid impact that killed the dinosaurs 66 million years ago. It survived Snowball Earth. It survived 5 mass extinctions. It has been hotter, colder, more acidic, and more radically different from what it is today. And every single time, it has found a way through. Given enough time, the ocean always recovers. So why are scientists so concerned about what is happening to it right now? The answer is speed. The ocean has always changed, but it has never changed this fast. The rate at which we are altering the ocean's chemistry, temperature, and ecosystems is, in some respects, faster than anything the geological record shows. And speed is everything when it comes to the survival of living things. Evolution takes time. Ecosystems take time to adapt. When change happens too fast, species simply can't keep up. The most fundamental problem is carbon dioxide. Every year, human activity pumps enormous quantities of CO2 into the atmosphere from burning fossil fuels, from deforestation, from industry. The ocean absorbs roughly 30% of that CO2. On the surface, that sounds helpful. But when CO2 dissolves in seawater, it forms carbonic acid. The ocean is becoming more acidic. Not dramatically, not yet, but enough to cause serious problems for the creatures that build their shells and skeletons out of calcium carbonate. Oysters, mussels, sea urchins, corals, and countless other species are finding it harder and harder to build and maintain their structures in more acidic water. For coral reefs in particular, this is an existential threat. Coral reefs cover less than 1% of the ocean floor, but support roughly 25% of all marine species. They are the most biodiverse ecosystems in the ocean, the rainforests of the sea, and they are bleaching. When ocean temperatures rise even slightly above their normal range, corals expel the microscopic algae that live in their tissues and give them their color and their energy. Without those algae, the coral turns white, bleached, and begins to starve. If temperatures return to normal quickly enough, the coral can recover. But if the heat persists, the coral dies. The Great Barrier Reef has experienced 6 mass bleaching events since 1998. The frequency is increasing. On top of acidification and warming, the ocean is also dealing with overfishing, pollution, and habitat destruction on a massive scale. An estimated 8 million metric tons of plastic enter the ocean every year. Large patches of floating debris have accumulated in the circular current systems of the Pacific, Atlantic, and Indian Oceans. Marine animals mistake plastic for food. It enters the food chain and works its way up through fish, seabirds, and marine mammals. Microplastics, tiny fragments broken down from larger pieces, have been found in the deepest trenches of the ocean and in the most remote Arctic waters. There is nowhere in the ocean that is completely untouched by human impact. But here is something important to hold on to. The ocean is also resilient. Where human pressure has been reduced, where fishing has stopped, where pollution has been cleaned up, where habitats have been protected, recovery can be rapid and dramatic. Marine protected areas consistently show higher levels of biodiversity than unprotected areas. Coral restoration projects, where fragments of healthy coral are grown in nurseries and transplanted onto damaged reefs, are having real successes in some locations. The science of ocean conservation has never been better funded or better understood than it is today. The ocean doesn't need us to save it in some grand, heroic sense. It will outlast us regardless of what we do. What it needs, what the millions of species that depend on it need, is for us to slow the changes we are driving and give it time to adapt. That is a choice we are still in a position to make. We have travelled a long way in this episode. From a molten, waterless rock 4.5 billion years ago, through the first rains, the first ocean, the first microscopic life, the transformation of the atmosphere, the freezing and thawing of an entire planet, the explosion of complex life, the shaping of the continents, the rise of human civilization, the first dives to the deepest point on Earth, and the challenges the ocean faces today. Every breath you take contains oxygen that was produced in large part by microscopic organisms in the ocean. The water in your body has been a comet, a cloud, a river, a glacier, and an ancient sea. The fish on your plate, the weather outside your window, the climate that makes your part of the world livable. All of it flows back, in one way or another, to the ocean. We live on a water planet. We have always lived on a water planet. And the story of that water, 4 billion years of it, is still being written. The ocean is not a finished thing. It is alive in the deepest sense of the word, and it is still changing, still moving, still shaping the world we live in, just as it always has. In our next episode, we will look at what happens when that ocean almost completely disappears, when the Earth becomes a frozen world locked in ice, and how the creatures living in it found ways to survive against impossible odds. Until then, thank you for listening.